Hello and welcome back to Math Class in Session. Today, solving quadratic equations. One interesting feature of quadratic equations is the fact that they can have no solutions or no x-intercepts like this one. That's a quadratic function that doesn't touch the x-axis. It has no x-intercepts. It can have one solution like this one x-intercept there highlighted, or it can have two x-intercepts or solutions, like that one does. Now, to solve a quadratic equation means to find the x-intercepts, or the zeros, or the solutions, or the roots. There's four names for these things. We call them x-intercepts for obvious reasons. They're called zeros because if you think about it, the y coordinate at one of these x-intercepts is 0. So that's why they call them zeros. Also, they call them solutions, or here's another one, roots. The word roots has to be taken in context. We're not talking about the roots of a tree. We're not talking about a square root. A new way to use the word roots is to refer to the x-intercepts of a function. Solving by factoring. A little bit of review of grade 10 here. Let's take a quadratic and solve it by factoring. Firstly, you must equate it to 0. Don't try to solve these things unless they're equal to 0. If we're going to solve by factoring, then we have to factor. Here comes the factoring skills. Another reason to learn how to factor was so that you could solve things by factoring. So we factor, and it might be difference of squares, or it might be tall brackets factoring, or it might be group factoring. Whatever the case may be, you have to factor it. Then we note that if there's a product is equal to 0, if AB equals 0, then either A equals 0 or B equals 0. If you think about it, 0 times B would be 0. So here we set this up so that it's AB equals 0. So we set these factors equal to 0, at least mentally, and say x minus 4 equals 0, therefore x equals 4. Or possibly, if we said x plus 3 equals 0, x would equal minus 3. That's the idea of solving by factoring. Sometimes you'll be asked to check a solution. So let's check one solution. So this question might have said, solve and check. This is the proper form for checking a solution. First, you have to say what you're checking. I'm checking to see if x equals 4. Now, you can't just substitute x in here because we're checking to see if x does equal 4. So you can't just sub it in. You have to separate the sides by going left side equals. That's what LS stands for. Left side of this equation equals x squared minus x. And then plug in 4 for x, because that's what we're checking, and evaluate. And this one evaluates to 12. It's a very simple example. And then you separated the sides, so now we'll do the right side, which is very simple. That equals 12 as well. We notice that the left side equals the right side. We say this, and now we can confirm that yes, x equals 4. It's been checked. This is the proper form. Check. Say what you're checking, separate the sides, evaluate them both, and then say and conclude that therefore x equals what you checked. Or possibly conclude that it doesn't equal that. Now let's solve the same quadratic by using the formula. There's our quadratic. You must equal it to 0. And then we know that if ax squared plus bx plus c equals 0, then x must equal negative b plus or minus the square root of b squared minus 4ac all over 2a. I say all because this line, the fraction line, must extend underneath this minus b here. Going back to our quadratic, which we've equated to 0, so we've set it up to look like this. we can now say, well, a equals the coefficient on x squared, b equals the coefficient on x, and c is always equal to the constant term. And take those numbers, plug them into this formula, and evaluate. Notice a negative squared is always a positive, and this we have a negative 4 times a negative, which is going to turn out to be a positive 48. And of course, 48 plus 1 is 49. And the square root of 49 is 7. And we'll say 1 plus 7 over 2, that's 8 over 2, which is 4. Or 1 minus 7 over 2, that's negative 6 over 2, and that's negative 3. And of course, we get the same answer as before. That's solving by formula. Example, solve a quadratic equation. Now, this doesn't look like a quadratic equation. Solution. Multiply through by the common denominator. If we were to add and subtract fractions in this, our common denominator would be x plus 1 times x minus 1. We learned that when we learned to add and subtract fractions. So what we'll do as a strategy is multiply through by this common denominator, x plus 1 times x minus 1. And that means every term. X plus 1 times x minus 1 times the first term, minus 7 times x plus 1 times x minus 1 equals this term times x plus 1 times x minus 1. And you do this because, deliberately, we get this canceling happening. And we get this canceling happening. And now we have a much simpler problem to solve. Because if we can multiply the 6 into these brackets and get 6x minus 6, and we can multiply a product of conjugates here, we've got x squared minus 1 in brackets times this minus 7, of course. And over here we've got minus 5x minus 5. Notice the product of conjugates is a difference of squares. These things never go away. Multiplying it out, collecting like terms, equaling it to 0. And when you do equal it to 0, you notice that the squared term is negative. And if we're going to factor something, we'd like to have the squared terms positive. And so it's just a matter of multiplying through by negative 1. And all of a sudden, the squared term is positive. All the other signs changed as well. Now it's time to factor. And this will be tall brackets factoring, because there's a coefficient here on this 7. And so we'll need two numbers that multiply to 42 that are subtracting to 11. And so it'll be 14 times 3 is 42, and they're different by 11. And we'll put the signs on to hit the target of minus 11. So minus 14 plus 3 is minus 11. Divide off what divides off, and we've done it. We factored it. So through mathematical process, we've taken an equation, multiplied through by the common denominator, multiplied it out, collected like terms, factored it, and we've got AB equals 0 here. And so x minus 2 equals 0, or 7x plus 3 equals 0. And so x equals 2, or negative 3/7. Example. Create a quadratic function with x-intercepts located at 3 minus root 2, comma 0, and 3 plus root 2, comma 0. We notice that these are compound coordinates, meaning it's a single x coordinate that happens to have two terms. 3 minus root 2 is the x coordinate. And so we need to create a quadratic function such that those are the x-intercepts. Solution. Now, it's a math problem, and it's maybe a new math problem to many students. So one strategy is to say, okay, I don't know how to solve this one, but I could think about it and say, well, suppose I wanted x to turn out to be 3, or x to turn out to be minus 2, which is a lot simpler than 3 minus root 2 and 3 plus root 2. Suppose I just wanted x to turn out to be a couple of numbers. Where do these numbers come from? They come from a factored version of a quadratic. I can put them into these brackets. Now, if I asked you what's the solution to this, I'm sure that many would say, well, x equals 3 or x equals minus 2, so we can work our way up. And where did this come from? It came from factoring a quadratic. So to find out which quadratic, we could multiply them out. Ah, this quadratic, when factored, is this, and so it has this for roots. So if you're given the roots, this is how you can find the quadratic, by putting the roots into brackets with an x and subtracting. X minus a root and x minus a root. And this is minus -2. So with that thought in mind, we can go back to our problem and say, well, we'll have to go x minus a root in brackets times x minus a root in brackets. X minus one root in brackets times x minus the other root in brackets. Now, notice I put the roots themselves into brackets because they're compound. They've got two terms. Now we can subtract within those larger brackets. Minus 3 and plus root 2, minus 3 and minus root 2. And now we have to multiply out a trinomial times a trinomial will give us 9 terms. So it'll be x times everything in here, minus 3 times everything in here, plus root 2 times everything in there. I've done it here. Pause the video, make sure that I did it right. And we'll notice that 3 terms times 3 terms is 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, as predicted. Now, many of these terms offset each other. We have a minus x root 2 and a plus x root 2. They offset each other. We have a plus 3 root 2 and a minus 3 root 2. They offset each other. Tidying it up, it looks like this. And root 4, of course, is 2. And there's our quadratic. I'm claiming that this quadratic has this for roots. Well, let's see if this is true. Let's find out. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Negative b, which is negative 6, plus or minus the square root of b squared, which is negative 6 squared, minus 4a, which is this one, c, which is that 7, all over 2a. Simplifying. Now, root 8, we've learned, is root 4 root 2. And, of course, that's 2 root 2. We could common factor out a 2 in the numerator. And leaving behind 2 times 3 plus or minus root 2 over 2. The 2's will cancel. And we have the x-intercepts being 3 plus or minus root 2. That would be 3 plus root 2 and 3 minus root 2. So the zeros are indeed as predicted.